Greetings everyone, my name is GiGi and this is Let's Build, wherein I build a LEGO set timed to different media and talk about the facts concerning the topic of the build. Today's build is the LEGO NASA Apollo Saturn V versus the documentary series Moon Machines. I will not be playing any of the audio for copyright reasons. The footage I am using from this docu-series is for science and educational purposes. I am also using a different microphone this time, so hopefully that mitigates some of the differences in volume I've been finding. Specifications on the LEGO set. You were born to explore the universe. Build and inspire the next generation of astronauts with LEGO space rockets and vehicles. Let's go. Display and roleplay with this majestic meter-high LEGO brick model of the NASA Apollo Saturn V packed with authentic details. It features 3 removable rocket stages, including the SIVB third stage with the Lunar Lander and Lunar Orbiter. The set also includes 3 stands to display the model horizontally, 3 new for June of 2017 astronaut microfigures for role-play creations of the moon landings, plus a booklet about the manned Apollo missions and the fan designers of this educational and inspirational LEGO Ideas set. Features a meter-high, approximately 1:110 scale model of the NASA Apollo Saturn V with a removable SIC first rocket stage with main rocket engine details, removable S2 rocket stage with rocket engine details, removable SIVB third rocket stage with Apollo spacecraft and rescue rocket on top of the whole spacecraft, plus 3 stands to display the model horizontally. The Apollo spacecraft features the Lunar Lander and Lunar Orbiter. Also includes 3 new for June of 2017 astronaut microfigures. Great for display and role-playing the manned Apollo moon missions. Includes a booklet about the manned Apollo moon missions and the fan designers of this set. This set includes over 1,900 pieces. Measures over 39 inches high and 6 inches in diameter. From the manual, The Apollo Program. On May 25, 1961, President John F. Kennedy challenged his country to safely send and return an American to the moon before the end of the decade. NASA met that challenge with the Apollo program. It would be the first time human beings left Earth orbit and visited another world. The Apollo program played a crucial role in the space exploration and made it possible to explore more distant worlds further in the future. The Apollo program consisted of 11 space flights. The first 2 missions, Apollo 7 and 9, were Earth orbiting missions used to test the command and lunar modules. The next 2, Apollo 8 and 10, tested various components while orbiting the moon, also taking photographs of the lunar surface. While Apollo 13 did not land on the moon due to a malfunction, a total of 6 other missions did and returned with a wealth of scientific data and almost 881.8 pounds of lunar samples. The first manned mission to the moon was Apollo 8. It circled around the moon on Christmas Eve of 1968. Just over 6 months later, on July 20th, 1969, the world witnessed one of the most astonishing technological achievements of the 20th century, when a NASA astronaut on Apollo 11 became the first human to set foot on the moon. The Apollo 11 mission lasted 195 hours, 18 minutes, and 35 seconds. About 36 minutes longer than planned. After lunar orbit insertion, the command module, or CM, and lunar module, LM, separated. While one crew member remained in the CM, which orbited the moon, the other 2 astronauts made the historic journey to the lunar surface on the LM. After exploring the surface and setting up experiments for 21 hours and 36 minutes, the astronauts returned safely to the CM and began the journey back to Earth. Saturn V. Saturn V was the most powerful rocket that had ever flown successfully and was used in the Apollo program in the 1960s and 1970s. The rocket was 363 feet tall and weighed 6.2 million pounds when fully fueled for liftoff. The Saturn V used the later Apollo missions and had 3 stages. Each stage would burn its engines until it was out of fuel and then would separate from the rocket. The engines on the next stage would fire, and the rocket would continue into space. The first stage had the most powerful engines, since it had the challenging task of lifting the fully fueled rocket off the ground. The first stage lifted the rocket to an altitude of about 42 miles. The second stage carried it from there almost into orbit. The third stage placed the Apollo spacecraft into Earth orbit and pushed it toward the Moon. Transposition, docking, and extraction. Shortly after the translunar injection maneuver that placed the Apollo spacecraft on its trajectory toward the Moon, the transposition and docking maneuver would be performed. This involved an astronaut separating the Apollo Command/Service Module (CSM) spacecraft from the adapter which fastened it to its launch vehicle upper stage, turning it around, and docking its nose to the Apollo Lunar Module (LM), then pulling the combined spacecraft away from the upper stage. The fan designers. With a shared passion for both space exploration and Lego building, Valerie Roach, aka What's Up Today, and Felix Stuyson, aka Sobfan, worked closely together to create their impressive Apollo 11 mission model for Lego Ideas. The most challenging part was the lunar landing module. I, Felix, tried building it at its smallest possible. I wanted it to fit in the half-cone parts as seen in the model, while still looking good and accurate. After that, we began building the rocket around it. We also tried to make the rocket as sound as possible, so Valerie included pillars and beams inside for structural integrity. It actually took quite a long time to finish the whole model. There were often times when one of us just abandoned the project for a few weeks and came back to it later. However, thanks to the fact that it is a collaborative project, it was always the case that one of us continued making progress on the project and remotivated the other. All in all, we would say it took us about a year to complete. We were surprised, and happy of course, when we learned our model would be the latest one in the LEGO's Ideas series. What we like about the LEGO Ideas platform is the feedback and support you get from the community. It's great to reply to comments, read suggestions, and improve your model in the updates. Of course, the chance of designing your own LEGO set is also really cool. LEGO designers: Michael Pisaki, sorry I said your name wrong, Carl Thomas Merriam, and Austin William Carlson are full-time LEGO designers and avid space enthusiasts, so this was a project they very much wanted to be a part of. As Michael explains, we were actually not asked. I was so excited when I heard that the project was potentially going to happen, and I told Carl about it because I knew he was also a space fanatic. We decided it would be really cool to work together since it is such a big model, so we approached the Ideas team about helping to develop the product. We were amazed by how big the actual model was and how it was able to separate into all the different stages and components. This was very difficult to implement in our final design, since we needed to make sure that the rocket was strong enough when connected together, but also easy to separate. Moving on to facts for the Saturn rocket itself. The Saturn V is a retired American super heavy lift launch vehicle developed by NASA under the Apollo program for human exploration of the moon. The rocket was human rated and had 3 stages, and was powered by liquid fuel. Flown from 1967 to 1973, it was used for 9 crewed flights to the moon, and launched Skylab, the first American space station. As of 2024, the Saturn V remains the only launch vehicle to have carried humans beyond low Earth orbit, or LEO. The Saturn V holds the record for the largest payload capacity to low Earth orbit at 311,152 pounds, which included unburned propellant needed to send the Apollo Command and Service Module and Lunar Module to the Moon. The largest production model of the Saturn family of rockets, the Saturn V, was designed under the direction of Wernher von Braun at the Marshall Space Flight Center in Huntsville, Alabama. The lead contractors for construction of the rocket were Boeing, North American Aviation, Douglas Aircraft Company, and IBM. 15 flight-capable vehicles were built, not counting 3 used for ground testing. A total of 13 missions were launched from Kennedy Space Center, 9 of which carried 24 astronauts to the moon from Apollo 8 from December 1968 to Apollo 17, December of 1972. Some background. In September 1945, the U.S. government brought the German rocket technologist Wernher von Braun and over 1,500 German rocket engineers and technicians to the United States in Operation Paperclip, a program authorized by President Truman. Von Braun, who had helped create the German V-2 rocket, was assigned to the Army's Rocket Design Division. Between 1945 and 1958, his work was restricted to conveying the ideas and methods behind the V-2 to American engineers, though he wrote books and articles in popular magazines. This approach changed in 1957 when Soviets launched Sputnik 1 atop an R-7 ICBM, which would carry a thermonuclear warhead to the U.S. The Army and the government began putting more effort towards sending Americans into space before the Soviets. They turned to von Braun's team, who had created the Jupiter series of rockets. The Juno 1 rocket launched the first American satellite in January of 1958. Von Braun considered the Jupiter series of rockets to be a prototype of the upcoming Saturn series of rockets, and referred to it as an infant Saturn. Saturn development. Named after the 6th planet from the Sun, the design of the various Saturn rockets evolved from the Jupiter vehicles. Between 1960 and 1962, the Marshall Space Flight Center, MSFC, designed a series of Saturn rockets that could be deployed for Earth orbit and lunar missions. NASA planned to use the Saturn C3 as part of the Earth orbit rendezvous method for lunar missions, with at least 2 or 3 launches needed for a single landing on the moon. However, the MSFC planned an even bigger rocket, the C4, which would use 4 F1 engines in its first stage, an enlarged C3 second stage, and the SIVB, a stage with a single J2 engine, as its third stage. The C4 would only need to carry out 2 launches to carry out an EOR lunar mission. On January 10, 1962, NASA announced plans to build the C5. The 3-stage rocket would consist of SIC first stage with 5 F1 engines, the S2 second stage with 5 J2 engines, and the SIVB third stage with a single J2 engine. The C5 would undergo component testing even before the first model was constructed. The SIVB third stage would be used as a second stage for the C1B, which would serve both to demonstrate proof of concept and feasibility for the C5, but would also provide flight data critical to the development of the C5. Rather than undergoing testing for each major component, the C5 would be tested in an all-up fashion, meaning that the first test flight of the rocket would include complete versions of all 3 stages. By testing all components at once, far fewer test flights would need to be required before a crewed launch. The C5 was confirmed as NASA's choice for the Apollo program in early 1962 and was named the Saturn V. The C1 became the Saturn I and C1B became Saturn IB. Von Braun headed a team at the MSFC to build a vehicle capable of launching a crew spacecraft to the moon. During these revisions, the team rejected a single engine of the V2's design and moved to a multi-engine setup. The Saturn V's final design had several key features. F1 engines were chosen for the first stage, while new liquid hydrogen propulsion system called J2 for the second and third stage. NASA had finalized its plans to proceed with von Braun's Saturn designs, and the Apollo space program gained speed. The stages were designed by von Braun's Marshall Space Flight Center in Huntsville, and outside contractors were chosen for the construction: Boeing, North American Aviation, Douglas Aircraft, and IBM for the instrument unit. Selection for Apollo lunar landing. Early in the planning process, NASA considered 3 methods for the moon mission: Earth Orbit Rendezvous (EOR), Direct Ascent, and Lunar Orbit Rendezvous (LOR). A direct ascent configuration would require an extremely large rocket to send a 3-man spacecraft to land directly onto the lunar surface. An EOR would launch the direct landing spacecraft in 2 smaller parts, which would combine in Earth orbit. A LOR mission would involve a single rocket launching into 2 spacecraft, a mothership, and a smaller 2-man landing module, which would rendezvous back to the main spacecraft in lunar orbit. The lander would be discarded and the mothership would return home. At first, NASA dismissed LOR as a riskier option, as space rendezvous had yet to be performed in Earth orbit, much less in lunar orbit. Several NASA officials, including Langley Research Center engineer John Houbolt and NASA Administrator George Low, argued that a lunar orbit rendezvous provided the simplest landing on the moon with the most cost-efficient launch vehicle and the best chance to accomplish the lunar landing within the decade. Other NASA officials became convinced, and LOR was then officially selected as the mission configuration for the Apollo program and announced by NASA Administrator James E. Webb on November 7, 1962. Arthur Rudolph became the project director of the Saturn V rocket program in August 1963. He developed the requirements for the rocket system and the mission plan for the Apollo program. The first Saturn V launch lifted from Kennedy Space Center and performed flawlessly on November 9, 1967, Rudolph's birthday. He was then assigned as a special assistant to the director of MSFC in May 1968 and subsequently retired from NASA on January 1, 1969. On July 16, 1969, the Saturn V launched Apollo 11, putting the first men on the moon. Specifications. The size and payload capacity of the Saturn V dwarfed those of all other previous rockets successfully flown at the time. With the Apollo spacecraft on top, it stood 363 feet tall and, ignoring the fins, was 33 feet in diameter. Fully fueled, the Saturn V weighed 6.5 million pounds and had a low Earth orbit, or LEO, payload capacity originally estimated at 261,000 pounds, but was designed to send at least 90,000 pounds to the moon. Later upgrades increased that capacity. On the final 3 Apollo lunar missions, it sent up 95,901 pounds to the moon. At a height of 363 feet, the Saturn V stood 58 feet taller than the Statue of Liberty from the ground to the torch, and 48 feet taller than the Elizabeth Tower, which houses Big Ben at the Palace of Westminster. For comparison, the Mercury Redstone launch vehicle that launched Freedom 7 was the first crewed American spaceflight, which approximately 11 feet longer than the SIVB stage and delivered less sea-level thrust than the Apollo Command Module's launch escape system, although the Mercury Redstone could maintain that thrust for much longer. The Saturn V was principally designed by the Marshall Space Flight Center in Huntsville, Alabama, although numerous major systems, including propulsion systems, were designed by subcontractors. The rocket used the powerful F-1 and J-2 rocket engines. During testing at Stennis Space Center, the force developed by the engines shattered the windows of nearby houses. Designers decided early on to attempt to use as much technology from the Saturn I program as possible for Saturn V. Subsequently, the SIVB 500 third stage of the Saturn V was based on the SIVB 200 second stage of the Saturn IB. The instrument unit that controlled the Saturn V shared characteristics with one carried by the Saturn IB. The Saturn V was primarily constructed of aluminum, or aluminium. It was also made of titanium, polyurethane, cork, and asbestos. Delicious asbestos. Blueprints and other plans of the rocket were available on microfilm at the Marshall Space Flight Center. The Saturn V consisted of 3 stages: the SIC first stage, the S2 second stage, or SII second stage, and the SIVB third stage, and the instrument unit. All 3 stages used liquid oxygen, or LOX, as the oxidizer. The first stage used RP1 for fuel, while the second and third stages used liquid hydrogen, LH2. LH2 has a higher specific energy per unit mass, than RP1, which makes it more suitable for higher energy orbits, such as the trans-lunar injection required for Apollo missions. Conversely, RP1 offers higher energy density, energy per unit volume, and a higher thrust than LH2, which makes it more suitable for reducing aerodynamic drag and gravity losses in the early stages of launch. If the first stage had used LH2, the volume required would have been more than 3 times greater, which would have been aerodynamically infeasible at the time. The upper stages also used small solid propellant ullage motors that helped to separate the stages during launch and to ensure that the liquid propellants were in proper position to be drawn into the pumps. SIC First Stage. The SIC was built by Boeing Company at the McCoud Assembly Facility, New Orleans, where the Space Shuttle external tanks would later be built by Lockheed Martin. Most of its mass at launch was propellant. RP-1 fuel with liquid oxygen as the oxidizer. The stage was 138 feet tall and 33 feet in diameter. It provided 7,750,000 pounds force of thrust at sea level. The SIC stage had a dry mass of about 303,000 pounds when fully fueled at launch. It had a total mass of 4,881,000 pounds. The SIC was powered by 5 Rocketdyne F1 engines arrayed in a quincunx. The center engine was held in a fixed position while the 4 outer engines could be hydraulically tuned with gimbals to steer the rocket. In the flight, the center engine was turned off about 26 seconds earlier than the outboard engines to limit acceleration. During launch, the SIC fired its engines for 168 seconds. Ignition occurred at about 8.9 seconds before liftoff, and the engine at cutoff. The vehicle was at an altitude of about 42 miles, was downrange about 58 miles, and was moving at around 7,500 feet per second. While not put into production, a proposed replacement for this first stage was the AJ260X. This solid rocket motor would have simplified the design by removing the 5-engine configuration and, in turn, reduced launch cost. SII Second Stage. The SII was built by North American Aviation at Seal Beach, California. Using liquid hydrogen and liquid oxygen, it had 5 Rocketdyne J2 engines in a similar arrangement to the SIC, and also used the 4 outer engines for control. The SII was 81.6 feet tall with a diameter of 33 feet, identical to the SIC, and thus was the largest cryogenic stage until the launch of the Space Shuttle in 1981. The SII had a dry mass of about 80,000 pounds. When fully fueled, it weighed 1,060,000 pounds. The second stage accelerated the Saturn V through the upper atmosphere with 1,100,000 pounds force of thrust in a vacuum. When loaded with fuel, more than 90% of the mass of the stage was propellant. However, the ultra-lightweight design had led to 2 failures in structural testing. Instead of having an inter-tank structure to separate the 2 fuel tanks, as was done in the SIC, the SII used common bulkhead that was constructed from both the top of the LOX tank and the bottom of the LH2 tank. It consisted of 2 aluminum sheets separated by a honeycomb structure made of phenolic. Yeah. It consisted of 2 aluminum sheets separated by a honeycomb structure made of It consisted of 2 aluminum sheets separated by a honeycomb structure made of phenolic resin. This bulkhead had to be able to insulate against 126 degrees Fahrenheit temperature difference between the 2 tanks. The use of a common bulkhead saved 7,900 pounds by both eliminating one bulkhead and reducing the stage's length. Like the SIC, the SII was transported from its manufacturing plant to Cape Kennedy by sea. SIVB Third Stage. The SIVB stage was built by the Douglas Aircraft Company at Huntington Beach, California. It had 1 Rocketdyne J2 engine and was used the same fuel as the SII. The SIVB used a common bulkhead to separate the 2 tanks. It was 58 8.6 feet tall with a diameter of 21.7 feet, and was also designed with high mass efficiency, though not quite as aggressively as the SII. The SIVB had a dry mass of about 23,000 pounds, and when fully fueled, weighed about 262,000 pounds. The SIVB was the only rocket stage of the Saturn V small enough to be transported by cargo plane, Aerospace Line's Pregnant Guppy. For lunar missions, it was fired twice. First for the Earth orbit insertion after second stage cutoff, and a second time for translunar injection. The instrument unit. The Saturn V's instrument unit was built by IBM and was placed on top of the rocket's third stage. It was constructed at the Space Systems Center in Huntsville, Alabama. This computer controlled the operations of the rocket from just before liftoff until the SIVB was discarded. It included guidance and telemetry systems for the rocket. By measuring the acceleration of the vehicle attitude, it could calculate the position and velocity of the rocket and correct for any deviations. After the construction and ground testing of each stage was completed, they were each shipped to the Kennedy Space Center. The first two stages were so massive that the only way to transport them was by barge. The SIC, constructed in New Orleans, was transported down the Mississippi River to the Gulf of Mexico. After rounding Florida, the stages were transported up the intracoastal waterway to the Vehicle Assembly Building, originally called the Vertical Assembly Building. This was essentially the same route which would be used later to ship Space Shuttle external tanks. The SII was constructed in California and traveled to Florida via the Panama Canal. The third stage and instrument unit was carried by the Aerospace Line's Pregnant Guppy and Super Guppy, but could also have been carried by barge if warranted. Upon arrival at the Vertical Assembly Building, each stage was inspected in a horizontal position before being oriented vertically. NASA also constructed a large spool-shaped structure that could be used in place of stages if a particular stage was delayed. These spools had the same height and mass and contained the same electronic connections as the actual stages. NASA stacked, or assembled, the Saturn V on a mobile launcher, which consisted of a launch umbilical tower with 9 swing arms, including crew access arm, and a hammerhead crane, and a water suppression system which was activated prior to engine ignition during launch. After assembly was completed, the entire stack was moved from the Vehicle Assembly Building, VAB, to the launch pad using the Crawler Transporter, the CT, built by the Marion Power Shovel Company and later used for transporting the smaller and lighter space shuttle, as well as the Space Launch System. The CT ran on 4 double-tracked treads, each with 57 shoes. Each shoe weighed 2,000 pounds. This transporter was also required to keep the rocket level as it traveled the 3 miles to the launch site, especially at the 3% grade encountered at the launch pad. The CT also carried the Mobile Service Structure, or MSS, which allowed technicians to access the rocket until 8 hours before launch, when it was moved to the halfway point on the crawlerway, the junction between the VAB and the 2 launch pads. The cost from 1964 until 1973, $6.417 billion was appropriated for the research and development flights of the Saturn V, with the maximum being in 1966 with $1.2 billion. That same year, NASA received its largest total budget of $4.5 billion, about 0.5% of the gross domestic product, or GDP, of the United States at the time. 2 main reasons for the cancellation of the last 3 Apollo missions were the heavy investments in Saturn V and the ever-increasing costs of the Vietnam War to the U.S. in money and resources. At the time frame of 1969 to 1971, the cost of launching a Saturn V Apollo mission was between $185 million to $189 million, of which $110 million were used for the production of the vehicle. Lunar mission and launch sequence. The Saturn V carried all Apollo lunar missions, which were launched from Launch Complex 39 at the John F. Kennedy Space Center in Florida. After the rocket cleared the launch tower, flight control transferred to Mission Control at the Johnson Space Center in Houston, Texas. An average mission used the rocket for a total of just 20 minutes. Although Apollo 6 experienced 3-minute engine failures, and Apollo 13 experienced one engine shutdown, the onboard computers were able to compensate by burning the remaining engines for longer to achieve parking orbit. Range safety. In the event of an abort requiring the destruction of the rocket, the range safety officer would remotely shut down the engines and after several seconds send another command for the shaped explosive charges attached to the outer surfaces of the rocket to detonate. These would make cuts in fuel and oxidizer tanks to disperse the fuel quickly and minimize mixing. The pause between these two actions would give time for the crew to escape via the launch escape tower, or, in later stages of the flight, the propulsion system of the service module. A third command, SAFE, was used after the SIVB stage reached orbit to irreversibly deactivate the self-destruct system. The system was also held inactive as long as the rocket was still on the launch pad. The startup sequence. The first stage burned for about 2 minutes and 41 seconds, lifting the rocket to an altitude of 42 miles and a speed of 6,164 miles per hour, and burning 4,700,000 pounds of propellant. At 8.9 seconds before launch, the launch stage ignition sequence started. The center engine ignited first, followed by opposing outboard pairs at 300 millisecond intervals to reduce the structural loads on the rocket. When thrust had been confirmed by the onboard computers, the rocket was soft-released in 2 stages. First, the hold-down arms released the rocket, and second, as the rocket began to accelerate upwards, it was slowed by tapered metal pins pulled through holes for half a second. Once the rocket had lifted off, it could not safely settle back down onto the pad if the engines failed. The astronauts considered this one of the tensest moments in riding the Saturn V, for if the rocket did fail to lift off after release, they had a low chance of survival given the large amounts of propellant. To improve safety, the Saturn Emergency Detection System, or EDS, inhibited engine shutdown for the first 30 seconds of flight. If all 3 stages were to explode simultaneously on the launch pad, in an unlikely event, the Saturn V had a total explosive yield of 543 tons of TNT, or 0.543 kilotons, which is 0.22 kilotons for the first stage, 0.263 kilotons for the second stage, and 0.068 kilotons for the third stage. Contrary to popular myth, the noise produced was not able to melt concrete. It took about 12 seconds for the rocket to clear the tower. During this time, it yawed 1.25 degrees away from the tower to ensure adequate clearance despite adverse winds. This yaw, although small, could be seen in launch photos taken from the east or west. At an altitude of 430 feet, the rocket rolled to the correct flight azimuth and then gradually pitched down until 38 seconds after second stage ignition. This pitch program was set according to the prevailing winds during the launch month. The four outboard engines also tilted toward the outside so that in the event of a premature outboard engine shutdown, the remaining engines would thrust through the rocket's center of mass. The Saturn V reached 400 feet per second at over 1 mile in altitude. Much of the early portion of the flight was spent gaining altitude, with the required velocity coming later. The Saturn V broke the sound barrier at just over 1 minute at an altitude between 3.45 and 4.6 miles. At this point, shock collars or condensation clouds would form around the bottom of the command module and around the top of the second stage. Max Q sequence. At about 80 seconds, the rocket experienced maximum dynamic pressure. The dynamic pressure on a rocket varies with the air density and the square of relative velocity. Although velocity continues to increase, the air density decreases so quickly with altitude that dynamic pressure falls below max Q. The propellant in just the SIC made up about 3/4 of Saturn V's entire launch mass, and it was consumed at 13,000 kilograms per second. Newton's second law of motion states that force is equal to mass multiplied by acceleration, or equivocally that acceleration is equal to force divided by mass. So as the mass decreased and the force increased somewhat, acceleration rose. Including gravity, launch acceleration was only 1 1/4 gravity. The astronauts felt 1 1/4 gravity while the rocket accelerated vertically at 1/4 gravity. As the rocket rapidly lost mass, total acceleration, including gravity, increased to nearly 4 Gs at t plus 135 seconds. At this point, the inboard center engine was shut down to prevent acceleration from increasing beyond 4 Gs. When oxidizer or fuel depletion was sensed in the suction assemblies, the remaining 4 outboard engines were shut down. First stage separation occurred a little less than 1 second after this to allow for F1 thrust to tail off. 8 small solid fuel separation motors backed the SIC from the rest of the vehicle at the altitude of about 42 miles. The first stage continued on a ballistic trajectory to an altitude of about 86 miles and then fell into the Atlantic Ocean about 350 miles downrange. The engine shutdown procedure was changed for the launch of Skylab to avoid damage to the Apollo telescope mount. Rather than shutting down all 4 outboard engines at once, they were shut down 2 at a time with delay to reduce peak acceleration further. SII sequence. After SIC separation, the SII second stage burned for 6 minutes and propelled the craft to 109 miles and 15,647 miles per hour, close to orbital velocity. For the first 2 uncrewed launches, 8 solid fuel Ullage motors ignited for 4 seconds to accelerate the SII stage, followed by the ignition of the 5 J2 engines. For the first 7 crewed Apollo missions, only 4 Ullage motors were used on the SII, and they were eliminated for the final 4 launches. About 30 seconds after first stage separation, the interstage ring dropped from the second stage. This was done with an inertly fixed attitude, orientation around its center of gravity, so that the interstage, only 3 feet 3 inches from the outboard J2 engines, would fall cleanly without hitting them, as the interstage could have potentially damaged 2 of the J2 engines if it was attached to the SIC. Shortly after interstage separation, the launch escape system was also jettisoned. About 38 seconds after the second stage ignition, the Saturn V switched from a pre-programmed trajectory to a closed loop, or an iterative, guidance mode. The instrument unit now computed in real time the most fuel-efficient trajectory toward its target orbit. If the instrument unit failed, the crew could switch control of the Saturn to the command module's computer, take manual control, or abort the flight. About 90 seconds before the second stage cut off, the center engine would shut down to reduce longitudinal pogo oscillations. At around this time, the LOX flow rate decreased, changing the mix ratio of the two propellants and ensuring that there would be as little propellant as possible left in the tanks at the end of the second stage flight. This was done at a predetermined delta V, or delta 5. No, I think that is just delta V, because the V is not capitalized. 5 level sensors at the bottom of each SII propellant tank were armed during SII flight, allowing any two to trigger SII cutoff and staging when they were uncovered. 1 second after the second stage cut off, it separated, and several seconds later the third stage ignited. Solid fuel retro rockets mounted on the interstage at the top of the SII fired to back it away from the SIVB. The SII impacted about 2,600 miles from the launch site. On the Apollo 13 mission, the inboard engine suffered major pogo oscillation, resulting in an early automatic cutoff. To ensure sufficient velocity was reached, the remaining 4 engines were kept active for longer than planned. A pogo suppressor was fitted to later Apollo missions to avoid this, though the early 5th engine's cutoff remained to reduce G-forces. SIVB sequence. Unlike the two-plane separation of the SIC and SII, the SII and SIVB stages separated it with a single step. Although it was constructed as part of the third stage, the interstage remained attached to the second stage. The third stage did not use as much fuel to get to the LEO, low Earth orbit, because the second stage had done most of the job. During Apollo 11, a typical lunar mission, the third stage burned out for about 2.5 minutes until first cut off at 11 minutes and 40 seconds. At this point, it was 1,645.61 miles downrange and in a parking orbit at an altitude of 118 miles and velocity of 17,432 miles per hour. The third stage remained attached to the spacecraft while it orbited the Earth 1.5 times, while astronauts and mission controllers prepared for translunar injection, or TLI. For the final 3 Apollo flights, the temporary parking orbit was even lower, using the Oberth effect to increase payload capacity for these missions. The Apollo 9 Earth orbit mission was launched into the nominal orbit consistent with Apollo 11, but the spacecraft were able to use their own engines to raise the perigee high enough to sustain the 10-day mission. Skylab was launched into a quite different orbit, with a 270-mile perigee which sustained it for 6 years, and also a higher inclination to the equator. The lunar module sequence. On Apollo 11, TLI came at 2 hours and 44 minutes after launch. The SIVB burned for almost 6 minutes, giving the spacecraft a velocity close to the Earth's escape velocity of 25,053 miles per hour. This gave an energy-efficient transfer of lunar orbit, with the Moon helping to capture the spacecraft with a minimum of CSM fuel consumption. About 40 minutes after TLI, the Apollo Command and Service Module, or CSM, separated from third stage, turned 180 degrees, and docked with the Lunar Module, the LM, that rode below the CSM during launch. The CSM and LM separated from the spent third stage 50 minutes later in a maneuver known as transposition, docking, and extraction. If it were to remain in the same trajectory as the spacecraft, the SIVB could have presented a collision hazard, so its remaining propellants were vented and the auxiliary propulsion system fired to move it away. For lunar missions before Apollo 13, the SIVB was directed toward the Moon's trailing edge in its orbit so that the Moon would slingshot it beyond Earth's escape velocity and into solar orbit. From Apollo 13 onwards, controllers directed the SIVB to hit the Moon. Seismometers left behind by previous missions detected the impacts, and the information helped map the internal structure of the Moon. Saturn V displays. There are 2 displays at the U.S. Space and Rocket Center in Huntsville. SA-500D is on horizontal display made up of its SICD, SIIFD, and SIVBD. These were all test stages, not meant for flight. This vehicle was displayed outdoors from 1969 to 2007, was restored, and is now displayed in the Davidson Center for Space Exploration. Vertical display was built in 1999, located in an adjacent area. There is one at Johnson Space Center, made up of the first stage from SA 514, the second stage from SA 515, and the third stage made from SA 513, which was replaced for flight by the Skylab workshop. With stages arriving between 1977 and 1979, this was displayed in the open until its 2005 restoration, when a structure was built around it for protection. This is the only display Saturn consisting entirely of stages intended to be launched. Another one at the Kennedy Space Center Visitor Complex, made up of SICT, the test stage, and the second and third stages from SA 514. It was displayed outdoors for decades, then in 1996 was enclosed for protection from the elements with the Apollo/Saturn V Center. The SI stage from SA 515, originally at the McCoud Assembly Facility in New Orleans, is now on display at the Infinity Space Center in Mississippi. The SIVB stage from SA 515 was converted for use as a backup for Skylab and is on display at the National Air and Space Museum in Washington, D.C. Since this set includes a micro lunar lander and command module in a water tile to represent splashdown after return to Earth, I will also give a micro discussion on these machines. To learn more about the Lunar Lander, please visit my LEGO Lunar Lander video, where I go in depth on the set and the machine. The Apollo Lunar Module, or LM, originally designated the Lunar Excursion Module, LEM, was the Lunar Lander spacecraft that was flown between lunar orbit and the Moon's surface during the United States' Apollo program. It was the first crewed spacecraft to operate exclusively in the airless vacuum of space and remains the only crewed vehicle to land anywhere beyond Earth. Operational profile. At launch, the lunar module sat directly beneath the Command and Service Module, CSM, with its legs folded inside the spacecraft to LM adapter, or SLA, attached to the SIVB third stage of the Saturn V rocket. There it remained through Earth parking orbit and the translunar injection rocket burn to send the craft toward the Moon. Soon after TLI, the SLA opened and the CSM performed a maneuver whereby it separated, turning around, came back to dock with the lunar module and extracted it from the SIVB. During the flight to the Moon, the docking hatches were opened and the lunar module pilot entered the LM to power up temporarily and test all the systems except propulsion. The lunar module pilot performed the role of an engineering officer, monitoring the systems of both spacecraft. After achieving a lunar parking orbit, the commander and LM pilot entered and powered up the LM, replaced the hatches and docking equipment, unfolded and locked its landing legs, and separated from the CSM, flying independently. The commander operated the flight controls and engine throttle, while the lunar module pilot operated other spacecraft systems and kept the commander informed about system status and navigational information. The command module pilot visually inspected the landing gear. The LM was withdrawn to a safe distance, then rotated until the descent engine was pointed forward into the direction of travel. A 30-second descent orbit insertion burn was performed to reduce speed and drop the LM's paraloon to within about 50,000 feet of the surface, about 260 nautical miles uprange of the landing site. As the craft approached paraloon, the descent engine was started again to begin powered descent. During this time, the crew flew on their backs, depending on the computer to slow the craft's forward and vertical velocity to near zero. Control was exercised with a combination of engine throttling and attitude thrusters, guided by the computer with the aid of landing radar. During braking, the LM descended to about 10,000 feet, then, in the final approach phase, down to about 700 feet. During final approach, the vehicle pitched over to near vertical position, allowing the crew to look forward and down to see the lunar surface for the first time. Astronauts flew Apollo spacecraft manually only during the lunar approach. The final landing phase began at about 2,000 feet uprange of the targeted landing site. At this point, manual control was enabled for the commander, who had enough propellant to hover for about 2 minutes to survey where the computer was taking the craft and make any necessary corrections. If necessary, landing could have been aborted at almost any time by jettisoning the descent stage and firing the ascent engine to climb back into orbit for an emergency return to the CSM. Finally, one or more of the three 67.2-inch probes extended from the footpads on the legs of the lander touched the surface, activating the contact indicator light which signaled the commander to shut off the descent engine, allowing the LM to settle onto the surface. On touchdown, the probes would be bent as much as 180 degrees, or even break off. The original design used the probes on all four legs, but starting with the first landing, the LM-5 on Apollo 11, the one at the ladder was removed out of concern that a bent probe after landing might puncture an astronaut's suit as he descended or stepped off the ladder. The Apollo 11 command module, Columbia, was the living headquarters for the three-person crew during most of the first crewed lunar landing mission in July 1969. On July 16, 1969, Neil Armstrong, Edwin "Buzz" Aldrin, and Michael Collins were launched from Cape Kennedy atop the Saturn V rocket. This command module, number 107, manufactured by North American Rockwell, was one of three parts of the complete Apollo spacecraft. The other two parts were the service module and the lunar module, nicknamed Eagle. The service module contained the main spacecraft propulsion system and consumables, while the lunar module was the two-person craft used by Armstrong and Aldrin to descend to the moon's surface on July 20th. The command module is the only portion of the spacecraft to return to the Earth. It was physically transferred to the Smithsonian in 1971 following a NASA-sponsored tour of American cities. The Apollo CM Columbia has been designated a milestone of flight by the museum. The aircraft carrier USS Hornet, under the command of Captain Carl J. Seiberlich, I'm sorry, I probably said your name wrong, Seiberlich, was selected as the primary recovery ship for Apollo 11 command module. Before dawn on July 24th, Hornet launched 4 Sea King helicopters and 3 Grumman E-1 tracers. Two of the E-1s were designated as Air Boss, while the third acted as a communications relay aircraft. Two of the Sea Kings carried divers and recovery equipment. The third carried photographic equipment, and the fourth carried the decontamination swimmer and flight surgeon. At the time of 1644, Columbia's drogue parachutes were deployed. This was observed by the helicopters. 7 minutes later, Columbia struck the water forcibly at 2,660 kilometers east of Wake Island, 380 kilometers south of Johnston Atoll, and 24 kilometers from Hornet. It was 82 degrees Fahrenheit with 6 feet seas, and winds at 17 knots from the east were reported under broken clouds at 1,500 feet, with the visibility of 10 nautical miles at the recovery site. During splashdown, Columbia landed upside down but was righted within 10 minutes by flotation bags activated by the astronauts. A diver from the Navy helicopter hovering above attached a sea anchor to prevent it from drifting. More divers attached flotation collars to stabilize the module and positioned rafts for the astronaut extraction. Moon Machines is a Science Channel HD documentary miniseries consisting of 6 episodes documenting the engineering challenges of the Apollo program to land men on the moon. It covers everything from the iconic Saturn V to the command module, the lunar module, the spacesuits, the guidance and control computer, and the lunar rover. It was created by the team that made In the Shadows of the Moon, in association with NASA, to commemorate the agency's 50th anniversary in 2008. It first aired in June 2008 in the US and UK and was released on DVD a year later in June of 2009. The miniseries features interviews with around 70 of the 400,000 engineers who worked on the Apollo program during the 1960s and early 70s. These interviews are intercut with archive film sourced by Footage Vault from NASA's various film archives stored at the Johnson Space Center in Houston, Texas, the Glenn Research Center in Cleveland, Ohio, and from the National Archives in Washington. The miniseries is narrated by actor Bill Hope. The music score was composed by Philip Shepard. The episodes: Episode 1 is about the Saturn V rocket. The first episode of this series documents the creation of the iconic Saturn V rocket, the story of the Saturn V moon rocket technology that joined the vision of World War II German rocket scientists with that of a generation of young, dedicated U.S. engineers. Episode 2, The Command Module. The second episode is centered on the construction of the Apollo Command Module and the setback of the Apollo 1 fire. Find out how engineers built the Apollo Command Module, a space that provided astronauts with food, water, communication, and protection to the moon and back. Episode 3, The Navigation Computer. The third episode details the story of MIT's work on the Apollo Guidance Computer. A look at how a group of computer scientists grappled with the challenge of a round trip to the moon in the days when computer code and software hadn't been invented. Episode 4, The Lunar Module. The fourth episode features the Grumman project to build mankind's first true spacecraft, the Apollo Lunar Module. The story of the engineers who built one of the greatest engineering feats in history, the lunar bug, and how they dealt with the demands of weight restrictions. Episode 5, The Spacesuit. The penultimate episode focuses on the teams that created the remarkable Apollo pressure suit. To survive outside of a spacecraft, a spacesuit is required and needs to protect from the hostility of space. 2 unlikely companies take on this challenge. Episode 6, The Lunar Rover. The series' final episode centers on the design and perfection of the novel lunar roving vehicle, carried to the moon on the Apollo J-class missions. The story of how a small group of engineers convinced NASA to build the lunar rover. As well as with all Apollo engineering, it represented a formidable task. Awards and nominations. Episode 2, the story of the command module, won a Grand Remy from the World Fest Houston International Film Festival in 2009. I chose this series because the Saturn V carried all the machines and more on its journey to the moon with the Apollo missions, not to mention that it was the most perfect length for this LEGO build. Total build time today, 4 hours, 23 minutes, 25 seconds. We got through 5 episodes and 33 minutes, 41 seconds of the 6th episode. If you want to see the documentary series in full with audio and at normal speed, please check out Moon Machines. Remember to like, subscribe, share, ring that bell, all the things for the YouTubes. Thank you.